All right, guys, welcome back. We are here for section 13, which is getting a lot more into the nitty-gritty of digital forensics, which is one of my favorite cybercrime topics. So this is going to be a good one. All right, so here's our funny internet picture of the day. Gotta love 4chan in the kind of way where like you should never, ever go to 4chan. Wretched hive of scum and villainy. Anyway, so the first step in the actual digital forensics process, once you've gathered your evidence, you've returned from the crime scene to your lab, you have all these, USB drives, computers, mobile devices, whatever. The first step is to do what's called imaging. As they learned early on in the digital forensics history of trying to get evidence from computers, you never, ever do your analysis on the original, because that analysis has a small but non-zero chance of modifying the original evidence. And once you've modified the original evidence, if you try to present that in court, the lawyer's going to be like, nope, it was modified from the original. There's no telling what changed. We can't trust any of this evidence, and the jury's going to believe them. So we make what is essentially a copy, but is much more thorough than what would normally happen on a computer when you copy from one to another. So this is called imaging to distinguish it from copying. First thing you need to know about imaging is you need to use what's called a write blocker. You plug your original evidence, whether it's a cell phone, whether it's a hard drive, USB drive, whatever, into a hardware write blocker. They also have software write blockers, but the hardware ones are a little more easy for the jury to understand. And essentially this write blocker makes sure that data only goes in one direction, from the original piece of evidence onto whatever device you're using to create the image. It is impossible, if you use a write blocker, for any data to go from your machine to the original evidence. Okay, it is a one-way only street. Data can only flow from the original evidence into your machine that you're doing the imaging on. That is very, very important, because again, we need to make sure that that original evidence does not get modified by this process in any possible way. You also need to make sure you create your image on what's called forensically sterile media, which in this case for digital forensics means the hard drive or whatever you're using to contain that image doesn't have any previous cases on it, doesn't have any places where old data can pop up in your analysis. It needs to be just whatever drive you're putting that image on needs to be clean. Okay? To make it clean, you use a process called wiping, which is much different than deleting. And we're going to talk all about why deleting doesn't really mean gone later in this section. But for now, wiping essentially means you go through and every single sector on that drive, whether it's a computer hard drive, a cell phone storage, a USB drive, whatever, with the wiping process, it goes through and it essentially writes everything to 0, then it writes everything to 1, then it writes everything to 0, then it writes everything to 1, usually 8 to 10 times. That makes sure that there is no data from the original drive or the original data still on there. Okay? Once you do that wiping process, the media you have is sterile. Okay? Now, there are two different ways you can do a copy or an image. The best, the one that you should always do if you have the option, is what's called a physical image. A physical image essentially goes into every single sector on that source drive, that original evidence, and it looks at every sector and says, is there a 1 here or a 0 here? Copy that over. Is there, next sector, is there a 1 here or a 0 here? Copy that over. This can take a long time though. Like if you have a modern, 1 or 2 terabyte hard drive, this can take, 8, 10, 12 hours. But that is worth it because you are making very sure that you are getting every single piece of data. Sometimes though, especially with like mobile devices, you can't get a full physical read on the drive. You have to do what's called a logical read, which is essentially only copying over kind of the files that the file system knows are there. So if I opened up my computer's, Windows Explorer right now, that shows all the files that my Windows operating system thinks are on my hard drive. Technically, that's not all of them, but it's a lot better than nothing. So if all you can get is a logical image, do that. But if you have the option of doing the physical, do the physical. Logical, obviously, since it's doing a lot less work, that is a lot quicker, a lot faster. But once we've created our image, we need to make very, very, very sure that the original drive and our new image that we're going to do our analysis on are the exact same. Not one single bit has been changed. If there's a single 1 or a 0 that's been changed between the original and our image, it's no good to us, right? Because any defense lawyer is going to be able to say, well, they changed at least something. We don't know what they changed. Maybe they changed the dates of when this happened. Maybe, this evidence is now useless. Most of the time, if there is a change between the original and the image, it's an input-output error, or an I/O error, which just means it got read wrong. But those are very rare. In my years of teaching digital forensics and doing digital forensics, I don't know if I've ever seen a problem or an input-output error. But they are possible, so we do need to check and make really, really sure. The way we do that is using a process called hashing. And we talked about that in one of the technical videos where hashing is used for passwords. But this is the exact same process. That hashing process is the exact same, but we're using it for a very, very different purpose. Okay? So with hashing, the very short version is you take any amount of data. It can be anything from one letter to the entire Library of Congress to all the ones and zeros on somebody's hard drive. You send it through this really complicated mathematical process. You would need a PhD in mathematics to even start to understand how this process works. It doesn't matter quite how the process works. The important part is you take that original data, you send it through this hashing process, and it spits out an output that is, it looks like okay, so this is a hash output right here, 7282EE09B, blah, blah, blah. That is what's called an MD5 hash, okay? Now, what's important about this process is if you put the original data back through that process again, it results in the exact same hash every time. Also, if you change even one teeny tiny little thing in that original input, the output hash at the end will be completely and totally different. So if we had the entire Library of Congress, all those books, all that data, all those letters, all those numbers, everything, we put that through the hashing process, every time we put that giant mound of data through a hashing process, it will result in the exact same hash at the end. But if we change even one letter, there's probably millions of pages in the Library of Congress. If we change one letter and then send it through that process again, the hash output at the end will be completely different. So, as such, if we hash the original drive and we hash our image and they pop out with the exact same hash, we can prove mathematically that these are the exact same. Not a single 1 or 0 has been changed, right? So that's what this image is from. Somebody was doing an image of something. I found this on the internet. So the computed hash is essentially the original device, the original image, and then the report hash, that's the hash of our image, right? And as you can see, they match. And not only do we do this once, we do that twice with two different hashing algorithms, right? So there's MD5, which is a very common hashing algorithm, and there's SHA-1, which is also a very common hashing algorithm. And both of them return the exact same hash for the original and the new one. I mean, they're different from each other, but that's because they're two different algorithms. But what's important is this one matches this one, and this one matches this one. Okay? So now we can prove in court that the image that we did our analysis on is exactly the same as the original device. Now, it is mathematically possible to have two different inputs that give you the same hash output. That's called a collision. But the way these work, MD5, SHA-1, SHA-256, all those different hash algorithms, the way they work, the odds of finding a collision are astronomical. A SHA-1 hash is more unique to a set of data than your DNA is to you. In other words, there is a higher chance that somebody out there in the world has the same DNA as you, just through sheer random chance, than there is of two different sets of data, two different inputs having the same SHA-1 output. Okay? So there's theoretically the possibility of a collision, but the odds of it are so incredibly astronomical as to be completely meaningless. Does that make sense? Okay. Now, these are very important terms for you to understand, and I'm going to explain them in two different ways. Okay? So on this slide, I'm going to explain them to you in just kind of a verbal way, and then on the next slide, I have a picture that might make it a little easier to understand. Okay? So the first thing you need to understand is a file system. A file system is essentially the rules for how data is going to be stored on any given hard drive. I believe I talked a little bit about file systems in the first technical video. Essentially, there's a few different ones that are popular. The one that Windows usually uses is called NTFS. The one that Macintoshes use is called HCFS. There's also FAT16 and FAT32. There's a few different file systems out there, but those are the really common ones. And they each store data in slightly different ways. They each have slightly different methods of indicating the beginning of a file and the end of a file, indicating what's free space and what's used space, all those things. But when we first buy our original hard drive, we put it in a brand new machine. You know, this is right out of the box. Nobody's ever used it before. The first thing we have to do is set a partition on a hard drive. The vast majority of the time, that partition is going to be as close to the size of that original physical hard drive as we can get. But a partition needs to be like essentially it needs to be an even number of kilobytes. And sometimes there's a few kilobytes left over where the physical hard drive has the space to do a few more, but the partition, because it needs to be a nice even number, isn't able to fill that space. So on most people's hard drives, the vast majority of the time, the partition is like 99.999% of all the space on that physical hard drive. Now, allocated space is the term used to describe the areas of that hard drive where the file system thinks data exists, right? So if I download a new video game and I install that video game on my hard drive, my file system and my operating system are going to look on my hard drive for enough unallocated space. In other words, space where there's not currently a file listed, and say, okay, I'm going to put the files that compromise that new video game into that unallocated space. Once it writes all those ones and zeros for all those files for that new video game, that space is now allocated space, i.e. my file system, my operating system, they know that there's something there. In unallocated space is space on that hard drive that's free. Your hard drive, your file system, your operating system, they think it's empty. And we'll talk about why it's not really later on. Unpartitioned space is that usually very small part of your hard drive that has not been set aside for a partition. It does not have a file system assigned to it. Slack space, so any given file, like a partition, has to take up a nice even number of sectors. Let's say it ends, 32 kilobyte chunks are usually a good cluster size. But let's say we want to save a file that's only 6 kilobytes large, right? It's a very small file. Our file system's rules say that no matter how small a file is, it has to take up at least 32 kilobytes worth of space. Okay? So we save our 6 kilobyte file. Our file system thinks, okay, that 6 kilobyte file is taking up this entire 32 kilobyte chunk called a cluster. But it's not really taking up the entire 32 kilobytes, is it? It's only got, what, 32 minus 6. So there's 26 kilobytes worth of space in there that's not being utilized. Our file system thinks it's being utilized because that cluster has that 6 kilobyte file in it. But in reality, there's 26 kilobytes worth of empty space in that area. And we can find evidence there. We're going to talk a little bit more about how that works later, okay? So I know this is really confusing. This is one of the most difficult things for a lot of people to kind of wrap their head around, the difference between all these different things, all these different terms, all these different ideas, because they're all similar yet different. So I made this picture to kind of get that across, okay? So the largest circle here, the black circle, that is our physical hard drive. That is everything, every single physical piece of machinery within that hard drive thing that we have inside our computer. Okay? That's the black circle. Usually, there is some very small amount of unpartitioned space, i.e. this is space on the physical hard drive that has not been assigned a file system. It's not been assigned a partition. It is not, essentially it's not currently being used to the best of your computer's knowledge. Okay? Again, the vast majority of the time, this unpartitioned space in the green is very, very, very small. A few sectors, that kind of thing. But that doesn't mean it's not useful. That doesn't mean it doesn't have evidence on it, which again, we'll talk about a little bit later. Now, the blue circle is the partition space. This is usually, not always, but usually as big as the physical hard drive can allow it, as big as the partition can become. So the green unpartitioned space I've kind of exaggerated in size for purposes of this demonstration. Usually it would be like 1 pixel's worth of unpartitioned space. But you never know. There might be a case where there's a large amount of unpartitioned space. And you can look there for evidence. And again, we'll talk about why. But the blue circle, that is our partition. The vast majority of the time, 1 partition per physical hard drive. But again, that doesn't necessarily have to be the case. You can have 2 or 3 or 5 or 10 different partitions on any one physical hard drive. I don't know why you want to, but you can. You can also have 2 or more physical hard drives with 1 partition. That's called a RAID system, and that's kind of above our pay grade for this class, but it is possible. So, the blue circle, this is our partition. This is the area that our file system has to work with. This is the area that our operating system can save files to. Okay? Now, the gray space is unallocated space, i.e. it's space that the operating system thinks is empty. It's the space that does not have a current file stored in it. In other words, it's the free space on your hard drive. If you go to Windows Explorer right now and look at your C drive, it'll say, you know, your drive is a 1 terabyte drive and you've got 600 gigabytes saved. The 400 gigabytes that has nothing saved on it is the unallocated space. The 600 gigabytes worth of files you have saved on it are the allocated space. That's the stuff that your file system has said, this area is for the specific use of this file, we can't use it for anything else. Okay? Slack space is a very, very small part of your allocated space where there might be some hidden or forgotten evidence within that very, very small space, because of the fact that files need to end in a nice even number of kilobytes, and if it doesn't, your computer just kind of assumes it does. Okay? So if you have more that's about as good as I can explain it with the problems of, recording a video lecture. So if you still have questions, please post them in the chat. I'll try to either explain it more, explain it again, explain it in a different way, or point you to resources that might help you understand this. But it is very important that you understand the difference between all of these different terms and how they're different and how they imply different things. Okay? So, with our analysis, there are two big proprietary programs that the vast majority of major digital forensics labs use. There's NCASE and there's FTK. FTK is the one that I'm way more familiar with, but NCASE is very similar. It does the same job, but it does it in a different way. There are also open source tools, and then there are a few other proprietary tools, but those two are the biggest ones. Those two are the ones that, if you can learn how to use them, you want to do digital forensics, you can learn how to use those. Those are the ones you probably should learn because they're the most popular, they're the biggest ones. They both have very cool features. Okay, one of those cool features is called a known file filter. A known file filter, so we talked about hashing for verification of images, right? You can also hash each individual file. Any one file, you can, send that through the hashing process and get the hash at the end. Now, there are two different uses for this known file filter. First off, there's the files we can ignore, right? The same files that everybody has on their computer. There's no real chance that they're gonna be forensically interesting, right? So, if you have on your, the really basic Windows files that everybody has, they're not evidentiary, they're not interesting, we don't care. We can use the known file filter to ignore those, to kind of shove them to the side. And that kind of cleans up the image of all the different files, so we can search through it more easily for the stuff we do actually want to find, right? So if we can start a database of all the files that we know aren't going to have evidence in them, but they're on everybody's hard drive or a lot of people's hard drive, and I don't want to have to sift through all this stuff to find, the evidence that I'm really looking for. So what I can do is start a database of ignorable files, the ones that I know aren't going to have evidence in them because of just the way they work in my experience and stuff. And then, not only for that case, but for future cases, those files, any files that match that hash, i.e. they're the exact same as the ones we used before and said these are completely ignorable, will be kind of automatically filtered out. And we don't have that straw to look for our needle in, right? The opposite end of that is the known file filter alerts. Those are the ones we know we want to see. We know that's important. So one of the major uses for this is things like child porn. The FBI and a few other agencies, a few other groups have just giant databases of hashes that are known child porn. And because you can't take the hash and work back to the original data, they can freely give out all these hashes, and nobody can use those hashes to recreate any child porn. But we can use that database of known child porn hashes, put them in our known file filter as alerts instead of ignores, and then every time we do a new case, FTK or NCASE or whatever program we're using automatically will hash each and every file that it finds on that computer. If the hash matches any of the ones from the database of this known child porn, it will throw up a big red flag and it'll be like, hey, look, this right here, it has the same hash as a child porn image. That's bad. You need to look at that. So it kind of brings those things to our attention as a useful tool in that digital forensics analysis. Make sure we don't pass over something that's important, something that previous cases have shown are important. Another important thing you need to know about is called file carving. File carving is essentially when the file system doesn't realize there's a file there for lots of different reasons, usually because it's deleted, but there are other reasons too. You can go in and look at the hard drive, look at all the different sectors, and based on the data that's there, figure out, oh, there's a file here. Maybe it was partially deleted, maybe it was all the way deleted, but the file system doesn't understand it's there, but the data is still there, and I can carve out and say, look, this data that is just sitting in these sectors, usually in unallocated space, that's a file. And I can tell FTK or Ncase, hey, this right here, starting here and ending here, those ones and zeros, that's a file. Treat it like a file. And FTK or Ncase will be like, okay, cool, and then put that file into their database. The good news is FTK and Ncase go through and do this automatically for you, so you don't have to do it manually anymore. You still can do it manually. There are cases where FTK or Ncase might miss something. You can do it manually if you want, but mostly this process is automated. And the way it works is every single file has a different header and a different footer. The header basically says this is the start of a file, and the footer says this is the end of that file. Okay? So if you know what you're looking for, you can just search for those file headers and say, oh, look, that's the beginning of a file that FTK doesn't realize is a file. Where does it end? Oh, look through. Oh, look, there's the end. Okay, so starting here and ending here, that's a file. FTK, trust me, this is a JPEG or an MP3 or whatever. And they'll say, oh, all right, we can treat that as a file now. So it's a way to find things that are gone. Okay? So here in this picture, you'll notice that it has this highlighted part, the FFD8 FFE0. That is the file header for a JPEG file, a .jpg, right? So this person has gone through and looked in hex instead of binary and found this file header and is now pointing FTK towards it and saying, look, this is the beginning of a JPEG file. You need to understand that this is the beginning of a JPEG file because that might be good evidence for me. So treat it like it's a JPEG file. And you tell it where that file is using this, offset 14FD. That's essentially where on the hard drive you're trying to tell the computer that this file starts. Okay? Each different file type has a different file header. So JPEG, the file header looks like this. .exes, they also have a file header, but it looks different. .pngs also have a file header, but they look different. You know, .txts, same thing. Each one of those different file extensions denotes a different file header, but they all have one. Okay? Does that make sense? All right. When we come back, I'm going to teach you a little bit more about deleted data, hidden data, forgotten data, all that stuff, what exactly we're looking for using these processes. Okay?